Hi guys, this is Jean-François Marie, Chief Solution Architect here at Kalray in France. Welcome to this presentation. It's about next generation data centers and composable architectures. We are very lucky this year at Kalray to have 4 sessions for SDC20. Two of my colleagues, Jean-Baptiste Rio and Rémi Goguet, will drive presentations around a true customer experience about classified data and NVMe-oF, and the other one about how we build and disaggregate HCI using our small storage adapter and composable architectures. I'm lucky also to drive 2 presentations, this one and another one running at the same time today, high performance Rocky TCP solutions for end-to-end NVMe communication. What about this presentation? So yeah, we talk about flash drive, we talk about moving forward, pushing bottlenecks, IO bottlenecks, compute bottlenecks, storage compute bottlenecks as well. At the heart of those architectures are x86. And we know those x86 architectures are really limited in order to handle IOPS, certainly when we embrace NVMe and SSDs. And we know there are alternatives. So the purpose of this presentation is to introduce you with the unique architectures, processor architectures, and device architecture we are building at Kalray in order to enable NVMe-oF and to offload such services. Then who am I? So I'm Jean-François. I've been 30 years in the storage industry. I've joined many companies such as Sun Microsystems, EMC and NetApp for the past 13 years in different roles. I was solution architect, managers, and at the end of that path, director of product and solution EMEA. I love technology. I have a degree in electronics, and I'm also very active in the community. And I've been a SNIA member for more than 10 years, and I ran the French organization for 2 years. It has been a while, so I'm coming back on that matter because I think this is important, standards and communities to share our knowledge. That's interesting when you run a virtual event, and I think I can say ubiquity exists. I'm lucky to, as I said, running 2 sessions, and usually say in the agenda when you see those 2 sessions at the same time, say this is impossible. This year, I see that it's possible because my 2 sessions are really at the same time. I'm lucky because it's recorded. However, I will be on Slack answering your questions, and I hope we will get a very nice interaction. So see you on Slack also to answer your questions. So why composable architectures? So we all understand that there is a big pressure on data centers design coming from a lot of perspective. Network traffic is increasing due to the IoT initiatives. CPU power is more and more demanding due to the AI and all those data algorithms needed to be run to take benefit of the data. More and more data has to be stored and analyzed. And obviously, security is a big threat. So really all those things combined may put a lot of pressure on x86. And we see that if we do that analysis, 25% of the x86 power is really dedicated to data-centric as an average in data centers. And this is increasing dramatically. And due to the different perspective and the different algorithm and data complexity, we understand that general purpose CPU are not the best way to go, right? We need to think about new design, new processing accelerators in order to accelerate treatment in data centers. When it comes to infrastructures, right? The past years have seen the rise of HCI to reduce complexity in terms of the hardware, the different components, network, CPU, and storage all tied together. However, it's really limited, and there are a lot of side effects. Disaggregation and composable or new trends in order to build new type of architectures is really get the devices out, get those interconnect ready to sustain all those different components, and build on the fly the resources you need, like kind of the hyperscalers. Take one CPU here, a GPU, some memory, some drives, and build on the fly the type of architecture you need for your application. Because as we know that one generic setup cannot fit all workloads, so we need really custom-based ease of programmability in order to get the most of the infrastructure to really serve well our the next generation applications. Sorry. So we have seen some ideas in terms of trying to disaggregate HCI. You know, the naming HCI 2.0, separating the two workloads which are compute and storage, right? The x86 handling compute and the x86 storage are now separated. Some vendors are going that path. Is that working? Kind of, right? Because what I've seen is the protocol behind is not well suitable to really handle the workload. Kind of iSCSI is not well suitable, right, for that. Even if it's really there's an ease of use for the systems, but the data centers not really embrace that path. They need to go to the next step now, right? So yes, HCI 2.0, a big load on the cluster, a big load on the interconnect. That's very complex. There's no scalability. Look at how many nodes you can handle safely. And this does not allow composability, right? You cannot choose your components. You cannot build whatever you want. You stick to a set of servers in a matrix. That's very complex. So that we really need something new, something to break those boundaries. And we think that composability is really the way to go. So this new approach is really flexible, right? API driven, completely automated, based on new protocols, and we'll come back on that. So what are the key composable components? We just said that we need a new generation of processor. We need new type of processing units in order to handle those complex data. At Kalray, we design processors, and Coolidge is our third generation of processor, massively parallel array. On the left-hand side, you see traditional CPU design, sharing I/O via ASICs. Very bad programmability, so poor flexibility in terms of how you can organize them to sustain the complexity of I/O you have, or the complexity of the algorithm you may run. On the right-hand side, this is what we have designed at Kalray. 10 years of research and development in order to get that out. 80 cores, completely independent, organized in 5 clusters. This is a fully programmable architecture, really power efficient, delivering less than 25 watts, using high-speed interconnect, 2 times 100 gig, really high performance, 25 TOPS, obviously including safety and isolation for the security threat we have mentioned earlier. Just a quick snap here about the design, right? From the core to the cluster to the chip. Third generation core, vilw, 64-bit core, floating point units, 16-bit, 32-bit, 64-bit, and coprocessor to run CNN networks. At the cluster level, right, we have 16 cores, plus 1 to handle safety and security. We have level 1 cache currency plus a shared level 2 cache. Very high bandwidth here, more than 600 gigabytes per second. When it comes to the chip itself, this 5-cluster architecture, all interconnected with 2 times 100 gig per second, sustaining PCI Gen 4 bandwidth and interconnected to DDR4 type of memory. So very powerful HARS architecture in order to leverage composability. So we have seen that AI is pushing the boundaries in terms of the I/O and the requirement in terms of the CPU. We are moving back to handle high parallelism. We need to access all the data in parallel to field all the cores to analyze the data. This is massive parallel treatment. Same with network. So data network are demanding that massive parallelism. And the good news is many core is a massively oriented type of architecture. With many cores we have, with the cluster organization. We need also to have fast access to memory in order to have a sub-microsecond or around microsecond type of response time. And with the large memory on chip, 20 meg, and those isolated cluster, we can handle safely that data in a very short amount of time. In order to handle IO-intensive data or IO-intensive compute, we have that network on chip interconnect handling 2 times 100 gig per second. On the one hand, coming from the outside and coming inside the machine, as I said, PCI Gen 4 by 16 in order to have a non-blocking architecture. The system is really compute intensive ready. We can handle more than one teraflop, up to 25 TOPS. So those are great numbers. And if you recall what we had in the past, how many x86 we needed to have that, it's impressive how fast the technology has moved to synthesize such a chipset. We can handle crypto acceleration at line speed, and we can do line rate with Solomon. So we are ready for the next generation algorithm. We are ready for AI. We are ready for data intensive computing and data security. And obviously, we have such an organization to give flexibility. As I said, control plane and management plane on the one hand, and data plane in the other hand. For storage management, we have dedicated one cluster for control and management plane, and we have the other 4 clusters to handle data plane. Obviously, this is the way we go. But if you want to run AI, we can change the settings and have 1 cluster for control, 2 clusters for I/O, and 2 clusters for AI. This is really flexible. Based on that processor, we have designed a new set of I/O adapters, and you need those new enablers in order to build composability, in order to leverage standard components. What is our smart storage adapter? So obviously a PCI card Gen 4 based on that processor I just described. On the top of it, we have developed a storage services, and this framework is named Access Core Storage, ACS, right? It delivers a set of services and is ready to be programmed to have others. Standard, we are offloading completely NVMe-oF, both TCP and Rocky. This is completely standard. And we are doing TCP termination so that we don't need an x86 to manage the TCP stack. We have remote management, out-of-band management using gigabit Ethernet, and we are Redfish and Swordfish compatible. So you can manage that card, whether it's in a server or manage that card through BMCs if you're in a GBAF, right? Using PCI features, we propose NVMe emulation for ease of use, right? Our device is seen as just a regular NVMe device. So you don't need specific drivers to take benefit of the card. You just need your OS to have the NVMe driver. And we have another great feature. We told you that we need to offload x86. and there is a big pressure on x86 for the I/O to be sustained. And with a peer-to-peer functionality enabled by NVMe, we have that unique features to completely offload the x86 to I/O management. So if you have a server with drives in, just plugging the card, running the card, you completely bypass the x86 when it comes to handling the I/O to the drive. This is really efficient, and you can get up to several hundred tens of percent of the CPU. So your x86 with Kalray solution will be really dedicated to application workload. This is a sneak peek of the card. Some figures in terms of performance. I will not go through all the details here, but you can see that if you run full line speed NVMe-oF at multi-million IOPS, you're going to busy the card 100%. However, if you run slowly, let's say 1 million IOPS per second over the length, you have free cores, so you can run extra services such as error coding, AI, convolution networks, etc., etc. So this is really interesting to see that we combine CPU, GPU, and DPU type of features in the same card. So we have a nice CPU, we have nice boards in order to get started with composability. Now, as we say that it's completely open, you need an open storage stack. First, you need something programmable, right? Standard language, very easy to be done. As I told you, we have separated control and management plane on the one hand. We have a small Linux running on 16 cores, and we have the data plane. We have a specific cluster OS to take benefit of the massive parallelism of the cores. It's a POSIX compliant OS, and we can run those 16 to 40, 64 core, right? Because I told you it's really flexible. In terms of efficiency, yes, we need to terminate all the sessions. We don't need the x86. We want to handle the full workload ourselves. And we want to enable true inline processing. So we don't need any x86 in order to get started. We can completely handle the full I/O load. And then we rely on standards. That's very important. Whether it's NVMe, NVMe-oF, TCP, or Rocky, this is really the basic. And I forget PCI because we provide PCI cards. In terms of the software APIs and toolchain, look at on the right hand side here. Traditional API, SPDK, BDEV, ODP for the network, standard libraries such as ISL for error coding, for instance. So really, everything we are doing is based on standards. That's very important. So access core storage is really our tool chain that we can help you with doing things in order to get composability ready. So if we have a look at the process organization and the software environments, on the right-hand side, control plane, 16 cores running Linux, and the left-hand side, the data plane, 64 cores to run the cluster OS, and you see the interaction with the different devices, right? So we have the control of the device on the right-hand side, and we have the I/O stack going to those devices on the left-hand side. So how have we designed the software stack, right? Very modular and flexible framework, and this is one of the implementation we are using quite commonly. Management side, SPDK to get the different components ready and to get the structure of the different components. On the left-hand side, data plane, two big stacks: networking stack to handle TCP and network offloading, and the storage stack in order to run NVMe emulation and NVMe driver. So really interesting here. Those stacks are obviously completely designed to take benefit of the 64 core and handle massive parallelism from the I/O we can see coming out and into the drives and out and in from NVMe-oF. Then obviously you understand, yeah, that's right, that's good. You do NVMe-oF, but you're not the only one to do so, right? And you do NVMe, yeah, but you're not the only one to do so. And obviously you run some algorithm, and I gave you some ideas about what we can do and how we can process data very fast. Offloading is obviously happening at the data plane level, right? We have that open data plane and this this network optimized stack, as I told you, right? This is the first way we do NVMe. So NVMe offloading is done in the data plane. Very easy, very straightforward, massive parallelism, as said. But now, as I told you, we can do other offloads, and those are some figures. Reach Solomon to do error coding. Of course, key calculation, hashing calculation, and you get here some very interesting numbers. And you can see that we are running gigabyte per second, very comparable to what we have in and out the balls. We want to make sure that the count is not a limiting factor. So we are really obsessed about performances to make sure that nonetheless we can sustain the maximum workload from the bandwidth you have on the network, maximum workload and IOPS you get from the drives, and the latency impact of our card is really minimum. So we are talking here in terms of tens of microseconds. So some figures here as a reference, and you can see if we run full speed read Solomon, it only takes 1.5 cluster. So it remains 3.5 cluster to do IO or to do other algorithm. So quite powerful system. And again, this is not using x86 at all. So massive offload of x86 calculation. So in summary, what do we have? We have a platform to move forward in terms of the design of new architectures. We have a platform to enable composable architectures. We have a platform to disaggregate things, to disaggregate HCI. And I do recommend to listen to Remy Gauguet's presentation around how do we disaggregate HCI architectures, providing a smooth data plane across the nodes. Obviously, we're going to leverage our MPPA processor architectures, and we are designing boards in order to do so. And one I've shown here is really about NVMe-oF offloading, proposing NVMe SSD performance through fabrics, through TCP, through Rocky. This is important. The second thing is, again, proposing an alternative to x86. If you have an x86 compute node, we can be seen as a companion to offload data services from that x86, right? If we sit in a GBOF environment, we don't need x86 at all, and we can handle 100% of the I/O very efficiently, million of IOPS from our boards. We are working on lowering the cost, and this is important in terms of the design. You're not stick to a single model of compute and storage. You don't need to buy very expensive storage architectures and storage devices. You can just take GBOFs, x86 compute nodes or storage nodes, networking, GPUs, etc. Get that all together into a fabric and build your own computer on the fly based on your needs. So you're going to build your architecture based on your application, but you will not make suffer your application based on the lack of the components you have for your architectures. So working on lowering your cost, efficiency for the data center. We mentioned fully flexible, right? Fully programmable data plane based on SPDK. This is quite useful. You'll be amazed to discover everything you have on GitHub for SPDK, right? We are using eraser coding, caching, and other algorithms, but you can do so, right? You can have your own algorithm, so you're not stick to us. And we don't want you have a black box. We don't want you buy a card and just be stick to what we propose. We will ensure that you have some very good algorithm we will have tuned for your usage, but we want to open the platform so that you can have your own services running on the systems. And then it's important for us, as I said, to follow standards. We want to be future-proof, and we are making sure that we follow standards. NVMe, PCI, NVMe-oF, and others to come, perhaps, if we need to. But we are making sure that we are running all those interoperability tests so that when you plug the card into your systems, we are really making sure that it's fully interoperable. So very important. Those are the four pillars of how we develop things at Kalray. So this is what we are doing for composable architectures, smart components in order to enable flexibility and full programmability. Thank you so much. It has been a pleasure to be on that session with you today. I hope you enjoy it. Please take a moment to read this session, and happy to have some discussion over snack. And I hope I'm happy to answer your questions. Take care. Bye-bye.